very nice talk. Thank you about going us through the whole process of implementing this project. And I have a couple of questions. So the first one is, I suppose the idea here is that the shared cores of the GPUs are used if the algorithm is written in next processing on the GPU. But in the GPU we also have art cores for accelerating retracing and tensor cores for machine learning stuff. Are they considered in this?
Yeah, excellent question. So modern CPUs have many different types of accelerators in them, like ray tracing cores, tensor cores, and other things. If, for example, you use the standard linear APIs, those will dispatch to GPU kernels that actually use the tensor cores very heavily. So for using those, that's the best part that we have right now. For low-level access inside parallel force to use things like tensor core and tensor cores, there is no one working on anything related to that.
Thank you. And the other question is, have you tried to implement the same algorithm using some native GPU API like CUDA and measure the performance between the native C++ and native CUDA? Is there a difference?
Yeah, so we did a few steps. So we didn't do a full rewrite, but because CUDA C++ just extends C++, we did some small comparisons about things like the cost of atomics, things like that. Like CUDA has more fine-grained atomics than C++ has. We even found huge performance difference in them. There are things that could allow you to plot, like fine-grained synchronization between threads within a GPU core that you can expose with C++ here. So those do make a difference, but we didn't have to do a full rewrite of the things, so I cannot really give you a number of what's the gap between CUDA and the parallels. For the example I showed you, the gap is pretty much zero, it's like a few percent. For the one that I showed at the beginning, and that was essentially doing adding to vectors, right? But like for more complicated problems, for this one I don't have it.
Thank you.
Hello. I have a couple of questions. First of all, thank you for the talk. Very informative for sure. I noticed that there are plans, but not anything specific for new parallelization strategy policy. Para_CUDA was listed as potential to come up in 2029. If you have any information, if not, we can skip this question. And second question, is there any benefit of nesting for each with parallel execution or parallel and sequential execution compared to just making a product and going in parallel to the code? Thank you.
Yeah, thanks for the question. So the first question is whether there are any plans for something like a parallel CUDA execution policy. I'm not aware of any plans. It's the first time I heard about it. The second question is whether there is performance impact of nesting different parallels with each other. Like in general, in most of the programming models, like OpenMP, the parallelisms, the happy path and the fast path is where you have a single flat parallel loop and try to expose as much parallelism as you can as part of that. Nested parallelism with OpenMP over here. Here with the parallelisms you can try, but most of the implementation, all of the implementation I know, will just perform a sequential loop instead of the device, so you don't gain anything from that. On OpenMP, you need to have nested parallelism and you will to see something from it.
Can you say a little bit about how a program adapts at startup to the computational facilities that are available to it?
So, if I understand the question correctly, it can detect CPUs versus GPUs, things like that. So today, we don't have any fine-grained control for where to run every algorithm. So it has to be picked like program-wide or at least translation unit-wide. And the runtime detects whether that's available, what's available, whether a GPU is there, and if not, it just falls back using the CPU. And if you don't request a GPU execution, it will just fall back to the CPU. So it's very basic, I would say. So I think with senders and receivers, we're going to have control. We have already things like execution contexts and schedulers, and we have built schedulers with things like CUDA strings in them and thread pools, where you can very precisely pick how you want to adapt your program to the computation. But until then, it's just programs code and very basic.
Thank you for your talk. So I have three questions. First question is about so the first question, if we talk about speed parallelization, it's not because before it's not allowed. Okay, if it talk about CPU parallelizations like AVX2. So first, if we just provide compilation flag for GCC or Visual Studio, it's try to compile your code with these instructions that make parallelism. But problems that I saw, for example, if we just change instructions like one after another, just switch them place, it's in some cases will make some better performance optimization. So compiler could not figure out that like, okay, if we switching it, for example, like several objects creations and after that several multiplications. So compiler could not figure out how to make it better. Second question is about like the GPU parallelizations. The bigger problem is bottleneck is when we copy the data to GPU. And if we have some small algorithm, we will spend more time for just copying to GPU and back. How you work with this? And the third question about n-body simulations. Did you think about approach like cellular automatons? That is kind of perfect for such kind of work, and it was a lot of work, including Steven Wolfram, that showed that, okay, so first we could use it, and secondly we could achieve parallelizations like 50-40x.
Yeah, thanks, Tom. I'm going to answer the first three, then one and two. So for this work, we don't do a demo. So we look at the most common algorithms for n-body. We didn't think about exploring anything else. Regarding the AVX question, if I understood correctly, you mean that the compiler sometimes may or may not pick the right instructions depending on the compiler flag or one passes, and sometimes one passes with an AVX flag that may actually not suffice to improve performance or to enable the compiler to use it. Did I understood the question correctly?
Not really. So changing instructions position, for example, like we have creating one object, after that, recalculating some position in array, after that adding to this element some value, and repeat this sequence like calculating positions and like 4 times. It's could not parallelize it good, but if like we move all calculations of the position in the first batch, and after that just adding this value, it's make better performance, like plus 10-15%.
Yeah, so I'm not that familiar with the CPU compiler side of this. You might want to open a bug if you're not seeing the performance you're expecting. Typically, when implemented properly, the sequence execution policy it's similar to OpenMP CMD. So if CMD CMD happens to solve your issue, then good. But if it doesn't, it's not going to do anything magical. You might still need to help the compiler by trying to extract computation and parallelizing it a little bit, like doing multiple particles per loop and so on. And I think the final question was, what about memory management? Like, what's the performance overhead of moving memory between the GPU and the CPU? And that's an important issue. Like the parallels today rely on something called unified memory or unified virtual memory. It's basically it's like migrating memory between different NUMA nodes. So in our implementation, the implementation detects which device, whether the CPU or the GPU, is accessing the memory and how often, and it will move it to the right place and it might leave it there. So if you're doing something like a million iterations of just going over all the particles, the first iteration you will see a hit because the particles may have been initialized in the CPU and they have to be migrated to the GPU, but then they are left there, and the next time you go to the algorithm, they are already there, so you don't pay this cost. All of this is automatic, and all of this depends on performance heuristics, so there are easy ways to treat the implementation and cause it to migrate pages back and forth. There are heuristics to prevent that, but in the talk I mentioned about how to analyze performance and optimize, I go a great level of detail into that. and how to avoid these things from how to detect them, and then how to write code in such a way that you actually help the implementation make right decisions about where to put memory in a heterogeneous system.
Yes, but like the question was a little bit different. So you
Okay, maybe you can take it offline because there's some context that I think I want to also give a chance for somebody else. There was another question by somebody else.
There was, but I think he wanted to ask basically the same thing. So.
Okay.
I want to ask, what are the main performance benefits or trade-offs for using ECS and C++ for parallel programming workloads?
ECS?
Entity Component System.
So we didn't use one here. Typically it's just better access pattern, better cache locality, easier to vectorize. But it's really application dependent, whether what type of layout you want to
But
do.
for the n-body simulation, will there be performance trade-offs or benefits?
Yeah, there can be many performance. Performance is very sensitive to how you structure your data. And every approach to structuring data will impact performance of this. So for things like how to store the coordinates of a point, you can store all of the x coordinates first, all of the y coordinates after, or store x, y, x, y, x, y, x, y. ECS help you with being able to change these choices quickly and experiment, which is good for performance in general. In this demo, we just did manually. We picked something that makes sense, and that's it.
Thank you.
Yes, thank the speaker again.